Welcome back to Thrive, your go-to channel for transforming health and revolutionizing indoor air quality in visionary environments. Today, we're coming to you from the Thrive Linkage Symposium, where we have the honor of hosting renowned guest lecturer, Professor Giorgio Buonanno. Join us as we delve into the crucial topic of airborne transmission of respiratory pathogens in classrooms, exploring the evolution from manual airing to personalized ventilation. Don't forget to like and subscribe to stay updated on our latest content, and leave a comment below to share your thoughts.
Good morning, this is last time, and thank you all media for this opportunity for me to share some of the work that we have done on the topic of the airborne transmission of respiratory pathogens. I will present this problem for a particular microenvironment that is classrooms. Try to show what we can do in order to reduce this airborne transmission from manual airing to personal ventilation. First of all, we have to start, in my opinion, from the big error of the health authorities during the pandemic. The health authorities neglected the importance of the airborne transmission. You can see the different position of the WHO in March 2020 and in December 2023, but completely different. You can see that now they consider ventilation important to minimize the spread of COVID-19, but also for influenza and other respiratory infections. But anyway, this message is not so clear because the airborne transmission was not fully accepted by health authorities. You can see here there was a kind of roadmap of the WHO that started on the 9th of July 2020 after a letter that we published with about 239 scientists. But what about now? Probably during this month, I say probably because we are getting probably from the end of the last year, we will have a kind of surprise, a gift from the WHO. The WHO will publish a couple of documents. The first one is the new terminology of the airborne transmission, of the transmission of the respiratory pathogens through the air. This is not only terminology, but it's a kind of piece of science that we are introducing to the WHO in order for them to accept the airborne transmission. The second one is a web app, and in this web app, any person could estimate, could assess the airborne transmission, the risk once a scenario is imposed. Anyway, we observed in the past a paradigm shift, for example, for the transmission of the pathogens in the water. And now, when we use that water, we are sure that the water is clean. We call for a paradigm shift in 2021 for the air. And I can say that this paradigm shift is on the way, because also the general dominant thinking of the disease is changing. In the past, for us, for health authorities, most of the transmission respiratory disease was through the air because of the miasma theory. But then there was a change in the paradigm shift But now we are sure that we will have another paradigm shift where the pathogens will be transmitted through the air. So a new chain. We are inside this change. So, but what is the airborne transmission? Let's see. Any subject for a teacher respiratory activity emits respiratory particles. Of course, an infected subject emits infectious respiratory particles. This emission can vary as a function of the metabolic activity or the respiratory activity, and of course, also as a function of the viral load of the subject. The airborne transmission can be at any distance, so at the short range and at the long range. You have to consider like a smoker, that of course close to a smoker there is a higher concentration of particles, but the smoke can be in the room, so I can inhalate this smoke also if I stay far from the subject. And this is very important to understand, because for the WHO, before this pandemic, there was only the possibility of the airborne transmission for the moment. Then the fluid dynamic is very complex. The emission is not of single particles, but the emission is a multi-phase jet. You have to imagine a kind of puff cloud that remains coherent in the environment. So the question is, can we assess a short and long range airborne transmission? This is similar to people that work in indoor air quality use models to estimate the impact of an indoor source, starting from the generation, then the exposure of people, the dose, and then the risk that is related to this exposure. As regards the airborne transmission, the main problem was the estimation of the emission and the generation and the emission of viral particles. This was a very important point, and this was developed during the pandemic with a model, and this emission is a function of the droplet of the particles volume emission, of the flow rate, and of course of the viral load. You can see from this graph that there is an increase of the emission from resting to standing, light exercise and heavy exercise, but also there is an increase, a very strong increase from breathing to speaking to loudly speaking. So in principle it's very complex to estimate this emission, but we can in some way have a kind of magic number. So on the basis of this emission, in this paper, in this work, we estimate the risk at close proximity. This is the distance between one speaking subject and the exposed subject. And you can see that the risk is a function, of course, of the distance, but also of the time of the exposure. So if I stay the distance of 1 meter for 10 seconds or 1 minute, the risk is very low. If this time increases, of course, the risk that increases. What about the risk assessment at the long range? This is completely different. In principle, the concentration of respiratory particles can be reduced because of the sampling of the particles, but we cannot manage this because of the inactivation of the viruses, for example. But as an engineer, the only way to reduce this concentration is, for example, with the ventilation. Ventilation means air exchange. It means air enters from outdoor to indoor and the same amount of air exits from indoor to outdoor. On the basis of this concept, we developed a tool in the mid of 2020, if I remember well. This tool allowed to estimate the risk for a scenario and on the hypothesis of the completely mixed box model approach. It means that there is a concentration of the virus, of the viral concentration that is the same in each point of the room, of the environment. This could be a very strong hypothesis for some environments, but for other, it works. The other problem in applying this tool is the assumption of reliable input parameters. And of course, if I will present the case study of the classrooms, so we need emission values for children of respiratory particles. This is something that we don't have a lot of data on this age range. So we performed a study and we aimed to estimate the respiratory particle emission rates from children during speaking. So we involved in this experimental study more than 400 children and speaking at two different intensity levels, so speaking and loudly speaking, and the children read the phonetically balanced word list that is here reported, part of the list. Of course, this is in Italian, but we are investigating what are the words that in some way emits more, but probably we should repeat this study in the countries. What are the main results? First of all, these results are similar to the ones that Lydia found in 2008-9 for codes. So you can see here a double peak of inhibition, something less than 1 micrometer at about 2 micrometers. And then there is an increase of the emission as a function of the sound pressure level. So a child that is loud speaking emits something like 10 times more than the same child that is speaking, 100 more in respect to the same child that is breathing. So another important question is, are the directional flows important for airborne transmission? And directional flows can transport viruses or respiratory pathogens from the infected subject to the exposed one. So, but there are some environments where this is very important. For example, car cabin. Why? Because in this environment, there is a high occupancy and generally not high level of ventilation. So the question is, can we adopt simplified models to assess the infection risk? So we perform another study with an experimental validation of a numerical model. You can see here some comparison between the experimental data in terms of velocity and the numerical ones. But what was the main aim of this study? to estimate the risk for a 30-minute journey in a car cabin by varying the scenarios. So imagine to change the position of the infected subject, the driver, or one of the passengers. Imagine to vary the ventilation rate inside the car cabin or the ventilation mode. You can see here that we have the streamlines in this very little environment are very important. For example, if the driver is the infected subject, when the higher risk is for passenger 2, so this one, not this one. But if I change the position of the infected subject, of course, I will have another position that is at risk. Another important consideration, and you can see that from CFD simulation, there is a variation of the risk among the passengers, and these risks are very different from the well-mixed condition. The simplified model that I show you in the previous slide. So in principle, in this environment, we are not able to use this hypothesis because the airflow is very, very important. And if I increase, if I have a very high, imagine to have the maximum ventilation flow rate inside this car, then the risk is very low for the passengers. And there is, if you decrease the ventilation, then the risk increase. But at a very, very low ventilation, the risk is practically the same and very similar to the well-mixed condition. This is the effect of the airflow. So what is now to our case study? What is the particle dynamics in classroom? We can, in principle, open the window in order to reduce not only the airborne transmission, but also the pollution in the classroom. And you can see from here that in this classroom, we open the windows every 20 minutes per hour. So there is an increase of the CO2 and then a decrease during the opening of the windows. But we can observe that the concentration, these are ultrafine particles, so very little particles. The concentration of ultrafine particles in indoor is, in this case, is very similar to outdoor, because of course I have a strong penetration of indoor particles from outdoor to indoor, because in classroom generally we don't have indoor sources of ultrafine particles in general. And you can see from here that if I increase the window opening time per hour, then the concentration, the indoor concentration will be very close to the outdoor concentration. And of course, I will have a decrease of the difference between the CO2, outdoor CO2 and indoor CO2. So I improve in some way the CO2, but this is not the same for ultrafine particles. For PM10, the situation is different, because PM10 is generated typically by the children with resuspension, with the movement. So if I open the window, in some way I can reduce the concentration in indoor. But you can see here that we didn't find a clear trend between the opening of the window and the concentration of PM10, because it depends on the activity of the children. So in this study that was performed before the pandemic, we developed a kind of retrofit. So we applied a mechanical ventilation system and imposed, you can see here, mean value of CO2 of 1000 ppm before the pandemic. This one, it was focused on pollution and not on airborne transmission. You can see that by imposing this CO2 value, and so this ventilation, we can observe a difference of the ultrafine particle concentration, so protection for the children. And also we don't have a lot of peaks of PM10 inside the room. So the typical dynamics in a classroom is that PM10 and PM25 is generated from indoor, and ultrafine particles come from outdoor. Yes. So can we reduce the airborne transmission just opening the window? This was another study that we performed during the pandemic with different scenarios you can see here. But by summarizing this concept, we have two possibilities. One is to apply mechanical ventilation. So if I estimate once the scenario is defined, the input parameter in the tool, for example, in the model, I can define the correct value of ventilation that reduce the risk to an acceptable value. So if I have a mechanical ventilation system, there is no need of a retrofit. But if I have only the possibility, you can see here that the steps, probably Alex will show this for the application of the tool, but we have to define the scenario, the number of the student, the time of exposure, and then we can estimate in this way a risk. But if I have only the possibility of natural ventilation, and this is a problem because I have to estimate the value of CO2, but I need to monitor, and I need, of course, to check how the internal concentration is in respect to the imposed value. This is a more complex procedure. So what about mechanical ventilation? In principle, mechanical ventilation it probably is the best solution for a classroom. In terms of airborne transmission, UV system, okay, they can work, and also filtration, air cleaners can work in some way, but the best solution, of course, is mechanical ventilation. And during the pandemic, health authorities asked to engineers to show if mechanical ventilation can be a solution to reduce airborne transmission. For us, of course, it is the solution, because for us, respiratory particles are particles like environmental particles. But we performed a study in Italy because the regional government of Marche region supported the installation of mechanical ventilation system in more than 300 classrooms during the pandemic. So we were able to have a different level of ventilation. We were able to monitor the infected subjects, and so this study was very, very important because it was performed during the pandemic. And what is the main result? You can see here that the relative risk, starting from the one referred to classroom with no mechanical ventilation, reduce in a strong way if I increase the ventilation rate per second. And another important aspect is that there is a very good agreement with these experimental epidemiological data and values that we can estimate with the tool, with the model. So what was the, why this study can be considered, this is not my definition, it's a definition of one US colleague. This was a kind of Halley comment, this study, not because it's an extraordinary study, but because we had at the same time waves of infections, Delta Omicron, different level of ventilation and the monitoring of infection. So we had the opportunity practically to monitor everything. So let me finish with the last measure that we can apply in order to reduce airborne transmission. Imagine these two subjects speaking, one in front of the other. Now imagine that this is an infected subject. Can you protect this one in general ventilation? No, because of the short range, close proximity. So there is a kind of big bang, a respiratory big bang from the mouth of the speaking subject. So the exposed subject will inhalate fresh particles, respiratory particles. So what was the idea? The idea is to consider a kind of mini air cleaner, portable air cleaner. Portable air cleaner doesn't mean that has a small flow rate. No. The idea is to create a region here, a volume that is clean. In which way? This is a patent, personal clear. So you can see here that the emission from this subject, these respiratory particles, cannot enter in this volume because this air cleaner is able to form a kind of umbrella around the protected subject. And we have checked that from a numerical point of view, this solution for the short range, and we found an efficiency of something like 95%. It's like a mask, but then we apply this idea also in a classroom. So if the infected subject is the teacher, then can I protect one of the students here? Yes, I can put one of these air cleaners in front of the subject. So particles are all around the room, but you can see that without air cleaner, the concentration is very low. If I put this air cleaner in front of the subject, the concentration is lower. Of course, the concentration will increase for the other students, but this is a personal solution. This was one of the comments of the reviewers to our model, but we cannot solve problems for everybody. And in this case, the efficiency, the protection was higher than 99% because it's more easy, because particle does not present high velocity. So what is now the last development? This is a kind of, imagine a kind of shower, air shower. So imagine to protect the subject that is in a fixed position. So we designed this this device, you can see here, the air enter in the device and then exit in an annular hole in order to have a jet like a cone all around the subject. So there is the shower on the head and then this protection all around the subject. So the subject is here, and in principle in this volume the concentration of particles is lower, much lower. And this is personal ventilation. I don't need a huge amount of flow rate, for example. So we of course measured the velocity of the device. This is the device that we, the prototype that we prepared. This is the hole. Imagine that the air exit from here, and the measurements are here reported. So all around this circle, there is the air, clean air that exit from the hole. And we found a very good agreement between the CFD simulation and the experimental measurements. Very good agreement. So the last test that we performed is a measurement of particles inside, ultrafine particles inside and outside this volume. Imagine in this room to put on the head of someone this device, then we can measure in the volume and outside the volume. You can see here there is a kind of difference, a good difference, 30%, okay, in terms of concentration of ultrafine particles. This for us is a starting point, because it's important to understand that this jet is able to create a kind of mini room, and a subject inside this mini room is protected, can be protected, but he is free, without any mask or without anything. We had also the emission at the center of this shower. Imagine here, of a clean flow rate with a swirl, so low velocity, in order to fill this mini environment with clean air. You can see that the efficiency after 1 hour start to increase. So it means that we can, in principle, manage, design these volumes in a very efficient way. So imagine a teacher in a classroom that is forced to use masks for all the day, for every day of the week. Of course, sometimes he's tired, the jet lag or something like this, but tired, and the mask is not used in a correct way. But what is the idea? The idea is to put over the head of this subject simply this device, and this subject will be protected when he's seated there. But this can be applied also in buses, the bus driver, because not only for respiratory particles, but also for environmental particles, because along the street there are a lot of pollution. So also for driver of truck, for example. So what are the take-home messages? We can assess short and long range airborne transmission of respiratory pathogens, and we can manage short and long range infection risk through engineering controls as ventilation and air distribution. Let me finish with a sentence that it's a kind of spoiler of a paper that is in press, because in my opinion, beyond the paradigm shift, now we are ready for a new approach that allows to address with a minimum of monitored parameters indoor air quality standards, and this is possible on a technological, social, and political levels. Thank you very much for your attention.
Thank you, Giorgio. We basically could finish the forum now because you've covered all the topics from the beginning to the end. So we could either stop here and say, okay, everything's covered, or we can say now we have to stay until tomorrow and expand on each of these topics. And most of these topics will be focused on specific presentations, like what you started with, that WHO terminology and area. Now, this is, as you can imagine, quite political. And once it's published, was supposed to be published on the 10th of December, hasn't. Apparently going to happen soon, and I know already about papers which are accepted to discuss this. So this will be as interesting, and we both have been involved with this process in the beginning. Area is supposed to be a super tool, super model. Will it? Maybe Alex will talk more about it. Super or not? So this in relation to risk assessment tools. So then when we go to the issue of ventilation, and we need to go beyond open the window, which for a long time and still has been promoted by the WHO, and not only, well, as society, open the window is not a solution, or not a full solution. Now, what do? We can say in many buildings we already have very good ventilation, mechanical ventilation. That's what Peter will present. There's a very good message for many organizations which operate buildings based on mechanical ventilation. But it can be better, and those who participated in the forum in Melbourne, when we discussed different types of ventilation compared to what we have now, in particular displacement ventilation, which we believe, it's evidence for this, that it's much better from many angles than mixed ventilation, which we have now. So this is also a focus of what we are doing. And the issue of personal ventilation. This is not a new topic. Since I started working in the field of indoor air, this topic was discussed. And I must say, I've been always kind of skeptical about this. In particular, the idea of having what I imagine personalized ventilation something blowing directly into my nose, like we experience often on planes, and then what we do, we turn off this because it's annoying. But this technology also has progressed significantly. And in addition to what Giorgio described and what will be hopefully taken over, we will be working with Danish colleagues where that concept was originally born some decades ago. And from what I understand, they it's already working in some big institutions, big banks in Copenhagen and Denmark. So that's another topic. But at the final slide, but it's not quite impressive, but almost impressive. It has to, paper in Science has to be shortened by one paragraph. And before the editor is happy with this, and it's the process started, the paper was, well, it will be 2 years in August, I think, when they started working. This paper, yeah, well, it was first submitted in April last year, but we started as a group in around August 2 years ago, with 41 authors. This was the most difficult, I'd say, project of all the papers we've published with this group, to achieve consensus of what will be the 3 pages in Science. It was unbelievable. Because this is so interdisciplinary, that with what some agree, others don't agree, others are not clear with, or we are almost there. So with this, yeah.
Sorry, are you ready for questions?
Yes.
Okay, thanks, Lydia. Great, that they covered so much. Thank you, Giorgio. I have a question about the personal care protectors, for want of a better word. Has anyone sort of swiped that system with the virus to see what? Oh, sorry. If you had, like, I'm just thinking of a picture of someone with a personal ventilator and it's pushing their expired air away from the person they're talking to. I'm just thinking about what will be important. And my question, I guess, is about virus survival in that scenario. Because it seems like what you're also doing is probably reducing thermite deposition of the viruses. So where something would be expired and fall on the table, it's being expired and then pushed up into the air. So has anyone modelled the viral load in the room if there's a scenario where multiple people have their personal air distributors and everyone's expired viruses are being pushed up? So you've reduced the thermite deposition of the virus, you've increased potentially the actual volume of aerosolized virus in the room. So then I guess what will be important is whether you've actually increased the survivability of the virus in the room by increasing the aerosolized virus rather than allowing thermite deposition. Has anyone looked at the actual virus in this scenario?
I think I'm looking this of course, but anyway, any scenario is different, and any virus is different. Any respiratory pathogens. COVID-19 was neglected at the airborne transmission. There are also some viruses, for example, Ebola, where for them the airborne transmission is not considered very strong.
No, that's all contact. Oh, it's contact transmission. But yeah, so
if I can,
yeah,
this is a very, very important aspect. What's happening with this, and in fact, this is one of the projects of the laureate to investigate this flow, because now we have the flow, general flow in the room, and in addition to the flow generated by whatever devices we use. So what's the interaction of this flow has to be discussed, and what's the optimal way of this flow. And what's being discussed now, one option is to deliver clean air to the and then this air is dispersed. But another option potentially is to remove air from that space and then take it away. So that's another option. But then if we consider this in the context of displacement ventilation, where it's not all mixed, but it's going up, so then the problem disappears. But this issue, what's happening with the flows, is the key one. And
consider that personal ventilation, in my opinion, is very complex. If you want to deliver directly clean air to the subject, then because of the velocity and the pressure, you will collect a lot of particles, also respiratory particles. So in principle, the concentration will be higher inside this airflow in respect to don't have airflow. So this is very complex. So this was the reason why we considered a kind of umbrella, not directly going to the subject.
Cone of silence, cone of
Yeah,
Now, in response to Wendy's question, when he talks about mechanical ventilation, I'm presuming he's meaning typical mixed ventilation. That's what, that's what.
Yes.
Because right now this is the only basically type of ventilation.
That's not a question then. Sorry, I find it fascinating because I'm learning all the time. This yeah. So if someone's in their cone of silence, so to speak, and they're hacking away and there's lots of influenza or whatever, I guess there's the opposite of my question then. Are you creating a focus of thermite deposition that they've left behind after they leave that seat? Has anyone thought of that?
Well, this way, in my view, this is, I can't imagine that this will be a major problem because most of these particles follow airflow. But those particles which are big enough to deposit, they will deposit anyway.
Yeah.
So that's, I would imagine that this probably won't affect this. This is your area.
But I think for these personal devices, the most logical first application would be stationary people removed from other groups. So it's not the scenario in the paper where there's a mass being ejected right into somebody's face, but bank tellers, situations at cashiers or a lecturer in front of the room, so that the immediate surroundings, those types of depositions are not as much of a concern as if it was there and it's being spread to everyone there. So I think that's where these can start, as well as be more practical versus everyone in this room having their own little.
Yeah, because I can imagine that just creates this giant cloud of viruses, right? Up near the ceiling somewhere.
There are, I've seen, I don't know where this was tested properly, devices where you just put like a helmet on your face and that is a filter. So then you are really in your home.
Yeah, absolutely. Yeah.
But that's what we want to do. That's a different question. Any other questions? Now we have 3 more people who haven't introduced themselves. And we had a brief introduction, so maybe we'll start with Richard then.
So I'm Richard Brown. I'm a professor of mechanical engineering here, and honestly mainly involved in the CRC rather than this linkage grant, but they're related. And I might hand over to a very new PhD student here at QUT. Do you want to?
Yeah, so I'm Justine Hapkis. I graduated in 2022 with a double degree in mechanical engineering and computational mathematics, and I just joined the PhD program with the ARC Training Centre. My first day was Monday, so very new.
Justine, we are very, very happy with this.
Right, let's do it. Dave Wainwright, I'm Director of Air Quality Sciences within the Queensland Government Department of Primary Science. Certainly, we have an interest in measurement of particles, and that's the PM10, PM2.5, particles. Where French is keeping an eye on this project because it fits in with that.
This is Dave puts what you are keeping an eye on this. Now from the broader government perspective, not necessarily state perspective, but national perspective, is that many departments are keeping an eye, because the question is which national department will be the one which will hopefully hosting or be responsible for this indoor air quality standards which we are talking about. And it's kind of suggested that the environment should be the one.
Yes, I mean, also probably looking at where all the health stuff comes together nationally is through the in-health. All the states basically have lab. So that bit would be one to target to get something addressed globally across all the states. So you'll get some states that are very interested, and you'll get some states that are too busy with other things. Through in-health, get it on the in-health.
And of course, this is a topic for another.
And I'm interested in your tack there, trying to get some indoor air quality standards out there. I mean, National Health and Medical Research Council was in that sort of that was many, many, many years ago. And did actually have some like guidelines, I suppose. But if you go and chase it up now, they've all been rescinded, and there's nothing that they said
Historically, that's how it started. Okay, I think we are just about time, so unless there's any pressing questions, we thank you, Giorgio.
Thanks for joining us at Thrive. Remember to like and subscribe for more valuable content in the future, and stay connected with us on our other social media platforms. Keep thriving with us, and we'll see you next time.